Now that we've learned how to find critical points and extreme values, maximums, minimums, we're ready to apply these ideas to some real life problems. Maybe we're interested in maximizing profit or minimizing cost, or maximizing the volume of something, or minimizing the time spent on something. So all of these would be looking for maximums and minimums to optimize whatever kind of thing that we're looking for. So let's use these ideas, and we have been asked to design a 1-liter can shaped like a right circular cylinder. We want to know what dimensions will use the least amount of material. So here I've got my cylinder, so I can visualize what we've got here, and it needs to be 1 liter. Well, the volume of a right cylinder is going to be the area of the base, which is circular, so that's going to be pi r squared multiplied by how high it is. But how does that relate to height, radius kind of thing? Well, 1 liter is 1,000 cubic centimeters, and so this will equal 1,000 cubic centimeters. Now what we're interested in doing is minimizing this surface area. We'll call it A. And what do we need to make the can? Well, we need something to make the bottom. That's a circle. That's pi r squared. And then the top will be the same. So we have 2 of those. Plus we need materials to go around the sides of the can. Well, if you cut this and opened it out, think of like a label off from a can. It would look rectangular, and it would be h high. And how long would it be? Well, if we had taken this and undid this, it would actually be this distance around here then, because that's what we spread out to get this length over here. So that's going to be the circumference of the circle, which is 2 pi r. So the area to go around the sides is going to be 2 pi r h. Now we have the area expressed as 2 variables, the radius and the height, and we just want one variable, but we have the connection between the variables right here. We could take this and solve it for h. H would be 1,000 over pi r squared, and then we could sub that in right here for h. I'm going to put it down below, so 2 pi r subbing in 1,000 over pi r squared for the h, and we can simplify this a little bit. Let's cancel the pi's, and one of these r's will cancel with one of these r's. So let's write down our area function we're trying to minimize. It's 2 pi r squared plus 2,000 over r. We're going to write that as an r to the minus 1 because we are interested in finding critical numbers or critical points. And so 2 pi is a constant. Power out in front, that's 4 pi. Decrease the power by 1. Power rule on this next one as well. Power out in front, decrease the power by 1. And actually I'm going to write that down here. It's going to be r to the negative 2, so we'll put it down here in the denominators. We would like to know when this equals 0. So when 4 pi r equals 2,000 over r squared. Now let's go ahead and multiply both sides by r squared. That'll make that an r cubed. And we could then solve for r. And that would give us 500 over pi and cube rooted. Now let's confirm we wanted to find a minimum. Let's make sure this is a minimum. So let's take a second derivative. That's going to be 4 pi and then plus 4,000 over r to the third. Remember that r is the radius, and so r is greater than 0. So the second derivative will always be positive for r's greater than 0. So that means it's always concave up. Well, then that means we do have a minimum when the radius is the cube root of 500 over pi. And we could find the height by subbing that in for r up here. Some of the possibilities could be a tall thin can or a short wide can, and this area function that we're trying to minimize, here is the graph, and you can see that we found this place where that area was at a minimum. So the optimal can size in order to use the least amount of material would be when this radius was the cube root of 500 over pi. Let's go ahead now and sort of summarize the steps that we took and steps we would want to take for all optimization problems. So the first step would be to familiarize yourself with the problem. So read through it so you can think about what you're going to be doing. It's always a good idea to draw a picture so you can visualize what's going on. In this last one we could draw the right circular cylinder, and whatever the situation is, a picture helps you to see the connection between the variables. Then we're going to introduce variables. In ours we ended up with the volume, and we had variables radius and height. Then we ended up with the surface area, variables of radius and height. You're going to write an equation for the unknown quantity. We wrote an equation for this area that we were trying to minimize. Then we found the derivative of that and we set it equal to 0 to find the critical points, and there was just one, and we confirmed then that it was a minimum. We didn't have any endpoints to our domain that we needed to test here because we did find that minimum. And so with all of the problems, sort of the setup is going to be following these steps. The problems could be drastically different, but the setup of going along with these steps is going to be the same. It's going to be several example videos following this video so you can see some of the many ways that we can optimize in a variety of settings.